Right. Good morning, everyone. Thank you for coming. Welcome. People are still coming in, so please take your seats, and we'll get started. All right. So my name is Sasha, and you may imagine it has something to do with the former Soviet Union. So I was actually born in Moldova, which is, not very far. And I speak Russian, but it's a lot easier for me to do the talk in English. But if after the talk you want to discuss something, I think we can easily talk in Russian if you prefer. I live in Israel. I've lived there since I was 6, so most of my life. And for many years, I've been working on .NET development on both Windows and Linux and mobile. And roughly 6 months ago, I've kind of moved to a different direction, and I've been working at Google since on machine learning and Python and completely different areas. But I haven't forgotten my roots, and so these are my roots, and I'm coming back a little to talk about them. But maybe in the future, I'll be doing other stuff more related to my current role. And this is a talk on debugging and profiling .NET Core on Linux. And generally, the fact that we can run .NET on Linux is something I would not have believed maybe 3 or 4 years ago. And the fact that there are tools that now support this experience and that we can use to debug and profile our applications is completely non-trivial. But these tools are also completely non-trivial, and this is why I felt this kind of talk is necessary, to explain how the same things that you can do on Windows and that you might have experience with on Windows are possible on Linux as well. So generally, the motivation is to look at profiling tools and techniques and how to apply them to .NET applications running on Linux. And I will have to talk a little about the Linux terminology and philosophy as well, because it's hard to understand how to choose tools and what to use if you don't know how the operating system thinks stuff is supposed to work. And towards the end, we'll also talk about debugging, specifically core dump or crash dump analysis, and how that looks like on Linux. And I think the reason this is interesting is that, first, it's just, I guess, curious how things work on a completely different platform that runs .NET. But from a more practical perspective, I think a lot of us will be considering or are considering Linux as our primary deployment platform because it's often cheaper and faster and offer consolidation with other runtimes and frameworks that you might be using. And so even though Windows as a server still has a good place, a lot of us are now using Linux as our deployment platform. And then, debugging, troubleshooting, profiling, understanding performance becomes so important. A quick disclaimer. I've done this talk a few times. I started doing it about 1.5 years ago. And some things have changed, some things haven't. What I'm talking about here should mostly work for you if you're using .NET Core 2-point-something, but changes might be coming in the future. And some of this stuff relies on undocumented features or stuff I just hacked together and put on my blog or on GitHub. And I wish I could say, things are getting so good, you don't need those hacks anymore. I've been saying it for a couple of years, and still, you need a lot of these hacks to get productive doing this kind of work on Linux. So let's talk about the platforms that now support .NET. .NET now runs more or less on Windows, Linux, and Mac OS. We're going to focus on Linux. And there's a few things that we want to be able to do. One is profiling, understanding where the time is going, understanding what the CPU is doing, what the system is doing. Another kind of activity is dynamic tracing. So without changing the code, without adding log statements, being able to understand what the application is doing in production without having to stop it, redeploy it, and so on. We also want to talk about core dumps and how to analyze them. So what to do if the application crashes in production or has a memory leak in production, and what we can do to analyze that sort of situation. And as you can see, the tools for doing these things are naturally different for different operating systems. And there are vendors trying to build tools that work across all these systems, commercial tools mostly, but what the platform provides is, of course, different for each platform. So it's beneficial to understand the platform a little, and we'll be doing some of that here. And finally, a couple of last disclaimers before we actually get started. A lot of the stuff I'll be showing you has different degrees of overhead. So for instance, CPU profiling is something that can be done with a relatively low overhead on both Windows and Linux, and so that's going to work pretty well, even in production. But if you plan to use some of the more advanced tracing tools, you should know they have an overhead. So enabling them in production might in itself change the behavior of your system. And that also applies not just to Linux, but also to Windows. Just keep this in mind in general when you use investigation tools like this. So let's start with a bit of terminology and then dive into specific tools. So sampling and tracing are two key terms in performance profiling and performance investigation. Sampling is when you don't look at every single thing the system is doing, but rather you let the system do its thing, you let the system run, and once in a while you interrupt the system and you look at what it's doing. So you're not continuously logging everything, you're just occasionally stopping the system and taking a snapshot. And that's what we do with high-frequency things, with high-frequency events that we can't record, we can't log, because there's so many of them. So we have to just look at the system once in a while and see what it's doing, and try to use statistics to extrapolate to the full behavior. So that's sampling, and we use that for CPU profiling, for example. When you profile CPU instructions, there's billions of them per second, so you can't record everything, you have to use sampling. Tracing is what you use when you have fewer events, not that many, so say thousands or tens of thousands of events per second, like web application requests or garbage collections or file accesses. This is the sort of thing you can actually record and then inspect, and you don't pay that much for recording thousands of events per second. So let's look at what pieces make the .NET tracing architecture or infrastructure. This is .NET Core running on Linux on top of the operating system kernel, on top of the CPU, and not all of this was built to support .NET Core. In fact, almost none of this was built to support .NET Core. It's just part of how Linux looks at profiling, tracing, inspection, troubleshooting. So the kernel, the CPU, the operating system libraries, they provide a lot of sources of information, which is useful if you develop .NET applications, but also useful if you build Java applications or Python applications or C++ applications and run them on Linux. So this is something just worth knowing in general. And then there are the .NET specific pieces, like the CLR events, such as garbage collections or just-in-time compilation, which are coming from the CLR. And there's stuff like event source, which is what you use on Windows as well to produce custom trace events from your application, and you can use those on Linux as well. So what I'm saying is you need to understand the system and how it wants to implement tracing if you want to do that effectively yourself. So let's look at the official story. And this has been the official story very shortly since .NET Core was released for Linux. This is what Microsoft has been saying you should do if you want to profile your application running on Linux. So here's what you do. First, you download a pretty long bash script and just put it on the production machine. And then you run that with an install argument, and it downloads and installs a bunch of stuff it needs. And it detects which system it's running on. So it knows if it's running on Red Hat or SUSE or Ubuntu. It downloads the right dependencies, which is pretty nice. And then you run PerfCollect, and you tell it to start recording. And there's some arguments to control what exactly you want it to do. Do you want to record a CPU profile? Do you want to record garbage collections? Do you want to record memory allocations? You have a little bit of control on what to record. And then, when the recording completes, you get a zip file, which you copy to a Windows machine. And then you download PerfView, which is a really cool tool that you can use on Windows to do a bunch of things. And then you open the zip file in perf view, and you look at it, and you now understand certain things. And this workflow works, but there's a reason why I put these emojis at the end. I think it's kind of weird, and maybe you and I, as originally Windows developers, I'm guessing, could get used to this sort of workflow, but a Linux software engineer or system administrator is not going to be very happy that they need to copy stuff over to Windows to analyze recordings, especially if we're talking about production systems. And so what machine are you going to download that to? So anyway, let's look beyond the official story, understand how the different pieces work, and hopefully you'll be more productive than what the official story allows. So perf, which is the tool used by PerfCollect, is the official Linux multi-tool for performance investigations. You use it for profiling, you use it for tracing, you use it to look at what the system is doing, you can use it for high-level statistics and very low-level stuff in your CPU. It's really a multi-purpose tool, and it's developed as part of the Linux kernel, so it's really not a .NET tool in any possible way. And the question is, can we make it work with .NET applications? So if you want to install perf, it's pretty easy. You do have to do it, of course. But then, here's how perf kind of works. So on the kernel side, perf has a component which is always available. It's just part of the operating system. This is this thing here called perf events. And it can receive events from a variety of different sources in the operating system. So it can receive events from hardware stuff like page faults or cache misses. It can also receive events from software components, like the operating system scheduler, which tells perf whenever there is a context switch between threads or a new process is created, and so on. If you know Windows tracing, this thing here is really ETW, event tracing for Windows, but that's on Windows, of course. So the closest equivalent on Linux is this, is perf. Now, the user side, the user space part, is a tool called perf, which you can run and instruct this kernel component to do a bunch of things for you. And the way perf works, and we'll come back to that a little later, is that the kernel part records a bunch of stuff into a file or into a memory buffer, and then you can process that information either in real time from the buffer or after the fact from the file. But most people use the file approach because it's a lot easier and there's a lot more tools that actually work that way, and not the real-time approach, which is a lot more sensitive. So that's the basic story. Now suppose you do something with perf, and I'll show you a couple of commands coming up later. What will almost immediately happen to you if you use perf with a .NET application, or really almost every application which has a just-in-time compiler? What will happen is that instead of meaningful information, you will see lots of addresses, lots of numbers. This is actually the stuff we care about. This is the functions in our application, but they will be showing up as just code addresses. Now, you might be familiar with this problem from Windows as well, but on Windows, a lot of tools just work around it. They can download stuff automatically to make this go away. And on Linux, you have to understand a little more about what's happening. So what's happening is that here's a stack trace of just some .NET program running on Linux. This is a stack trace. Read it, bottom to top, like you always read a stack trace. So it's got program.main, program.foo, and then that calls writeLine and goes into some other functions. On this stack trace, there's multiple types of functions. And understanding the function name, getting the symbols correct, is something that differs based on the type of the function we're talking about. So for instance, if on Linux, on your stack trace, you have a kernel function, like syswrite over here. This is a kernel function in the operating system kernel. You don't need to do anything magical to translate the address to a name. It's something the operating system just provides in a special file. You can just read it from there. Then you have unmanaged code, like C++ libraries, such as libc, the standard C and C++ runtime, and that's something .NET also uses, so that's part of your stack trace as well. So these yellow frames here and here, for those to translate addresses to names, you need something different. So on Windows, that would be PDB files, PDBs, right, symbols. On Linux, it's called debug info, but it's essentially the same thing. It's a file with address to name translations. So you need to download those. And these are often available with your distribution. So if you install Ubuntu, you also can install debug information for various Ubuntu libraries like this. Then we have the .NET stuff. And the .NET stuff, we have 3 types of .NET stuff in here. We have core CLR, which is native. This is C++ code, but it's part of .NET itself, the .NET runtime. So these 2 frames over here. For this stuff, you get the symbols, you get the debug information by either building from source, so you can build your own core CLR, and then you have debug information for core CLR, or there is a special tool recently released called .NET Symbols, which you can use to download this information on the fly. So that kind of works. The trickiest 2 pieces are the ones you really care about. My code, the green stuff here, and .NET Framework code. So this is C#, but it's slightly different, right? The really green stuff is my code, and the slightly less green stuff is .NET Framework. So for the .NET Framework code, again, there's some options, because .NET Framework is not just-in-time compiled by default. Once you install .NET Core on a machine, these assemblies, the .NET Core assemblies, are pre-compiled ahead of time to native code, so that at runtime you don't have to spend time on JIT compilation. So that is something that is great. It speeds up startup time, but it also means that getting the debug information becomes trickier. So again, there's different ways of getting across that. We're not going to look into any of this in detail, but there's instructions available. And finally, for the C# code you wrote, which you really want to show up in profilers and debuggers and other tools, for the code you wrote, there is a magic trick. You can tell the .NET runtime to automatically write out a file into the temp directory, which has your process ID in its name, and that file will contain translations of addresses to function names, so that, again, debuggers and profilers can use that information to understand what's going on your stack trace. So there's a lot of stuff you have to do. And PerfCollect, that script I mentioned, mostly does this, but it doesn't always work. So it's good to know, what your options are and where this information is coming from. And it's also important to understand that some of these things actually have an overhead. I just told you that you can tell the .NET runtime to generate these files for every function you have in your program while your program is running. So every function that gets JIT compiled is now written into a file. That is not super duper fast. It is just the first time, and it's not that big a file usually, but it is additional work that has to be done. Just keep that in mind for now. So having all these little pieces and blocks, where's my mouse? Having all these little pieces and blocks, I think we can take a look at what the profiling work looks like. And I know you might have expected like a beautiful UI profiler or something, but we're dealing with a production Linux system, so the terminal is our best guess. So the first line here, which I've highlighted just to be a little more readable, so the first line here runs my .NET application with this environment variable enabled. And this environment variable tells the .NET runtime to create these mapping files between addresses and function names. If you don't do that, you will not see any names in your profiler report. And then the second command is just a standard perf invocation. This is where you come back to Linux and you say, how do you profile on Linux? This is the command you need to run. You'll find it on every tutorial online. And now it actually would work for a .NET application. So what Perf Record does is it takes a snapshot of what your process is doing at a frequency of 97 times per second. So that's the F97 at the end. We point it to just your process using the P switch, and the G switch says we want stack traces. So you want to know what the program is doing, not just right now, but what the stack trace was that led to this point. So this is what we're trying to record. If you can see, and it doesn't really matter, but here you see that perf would say at this point, I'm recording, then I hit Control-C, and then perf says I've written out some information. Now this file, you can now take and analyze on the same machine or in a different machine, but you will need that debug information. You will need these files to analyze the recording. And so it's easiest if you just do that on the same machine. And this is what PerfCollect also would do for you in a way. So one way, and this is not what I recommend, but it's still here just for completeness, and this is again what you'd find on the perf tutorials online, is Perf Report. This is just a built-in command which takes that recording perf created and turns it into this beautiful, let's say beautiful, tree printed in your terminal. And you can sort of work with this if you have a very, very simple profile that has like 10 different functions and that's it. It is not going to realistically work for a larger application. And so this is where I recommend, and I'm not going to have time to talk about it in detail, but this is where I recommend that you take a look at flame graphs. If you haven't heard of flame graphs before, they look like this. And they try to take all this textual information presented as a tree and convert it to an interactive diagram, which looks like this. And you can understand why it's called a flame graph, because it looks kind of like fire and flames. The colors don't actually mean anything. So you can also do an icicle graph with, blue and green, or you could do just a grayscale graph, but it's less cool, and so we call it flame graphs, and we do red and orange and yellow. Or you could do like a blue and yellow patriotic kind of flame graph. But anyway, what a flame graph tells you is basically the same thing about what your code is doing, except it's organized in a slightly more readable way. And specifically, each rectangle you see is a function, and the wider the rectangle is, the more time you spent in that function. So I'm going to zoom in on this just a tiny bit. This is main, and this is some other function called fetch, and then process result, and so on. And as you can see from the general profile, they are pretty wide. So this is where my application is spending most of its time. But actually, if you look at this tower to the right, there's also some stuff which is not in the same stack, looks slightly different. And this is the garbage collector thread. BGC is background garbage collection. So this is a GC thread running GC in the background while your application is also doing work. And if you look at the process result function here, this is my code, but then we call into core lib, which is .NET Core, and that calls into some core CLR functions here, framed allocate string, slow allocate string. By the way, slow allocate string definitely doesn't sound like something I want to be doing, but I am. So slow allocate string, and then a bunch of other stuff on top of that is just allocating memory. So again, we're not going deep into what exactly is going on in this particular application, but just by the width of the rectangles, you can see what the program is doing most of its time. And by following the hierarchy from bottom to top, you can see where it's diverging into different paths. So flame graphs are quite useful. Again, I wish we could do a full talk on flame graphs, maybe some other time. And they're useful not just for profiling, they're useful for a lot of other scenarios. And to generate this flame graph, all I had to do is use another perf subcommand and a couple of Perl scripts I downloaded from GitHub. And flame graphs were invented by Brendan Gregg, who's a senior software engineer at Netflix. And he wrote these Perl scripts initially. And since then, flame graphs have found their way into a bunch of other products, including PerfView on Windows, which now also has flame graph support. So this was kind of in a nutshell how you do CPU profiling. And this is like the basics, the very basic profiling you have to do because you have to understand where the time is going. But there are some more interesting things you can do as well. So let's talk a little about those. This was a weird diagram. Something went wrong with my animations, you see. But anyway, let's cherish this. So what you see on top is what I told you before about perf. So the way perf works is some stuff is happening in the kernel, gets written into a file, and then you have some user space scripts read that file and generate some kind of report. Maybe a flame graph, maybe a histogram, maybe a JSON file that you send somewhere. But the point is, you write a lot of stuff to a file, and then you have to read that file. And that probably sounds a little suspicious, because that file is on disk. And if the rate of things, the rate of events is so high that the disk becomes overloaded with this writing, you will first slow down the system, but also start losing events. So if you do very high latency, low latency tracing, where events are happening every microsecond maybe, then writing everything to a file is not going to work. And the way Linux today is looking at doing this high-performance, low-latency tracing is using a different kernel mechanism, not perf, a different kernel mechanism called BPF, Berkeley Packet Filters. And again, we could do a full talk just about BPF, but we will not do that. BPF for us, for .NET developers, is just kind of like perf. It's yet another Linux kernel mechanism that can be used for tracing and profiling and recording information. The key difference is that perf in the kernel is a fairly simple component which receives information from somewhere and puts it in a file, but BPF allows you to have in the kernel a smarter component, essentially a full program that processes these events, takes out what you need, and stores only the statistics or the aggregated information. So you don't have to go through a huge file to just get some statistics, to do a histogram or to do stack traces or profiling like you have to do with perf. So this is BPF in a very, very brief introduction. And there's a bunch of tools on top of BPF, kind of like there are tools for perf. There are tools on top of BPF. And I have been contributing for a couple of years to an open source project called BCC, the BPF compiler collection, which is basically not a compiler collection. It is a tool collection. It is a bunch of tools that you can use on top of this kernel mechanism. And again, very little of this is actually .NET specific. Kind of like with perf. I was showing you how to use perf with a .NET application, but perf itself is not .NET specific in any way. Same thing with BCC and BPF. These are Linux tools. You can use them for Java, for Python, for Perl, for PHP, whatever, but you can also use them for .NET code. And some of the tools are just for fun. I put a lot of tools on this slide, and I'm just going to show you a couple of them, just so you get an idea of what's possible. So these are two tools called siscount and OpenSnoop, just as examples. These tools highlight why it's important to do a lot of work close to the source in the kernel instead of going through files. The first tool, this siscount tool, is a tool that looks at all the system calls your process is making, all the interactions with the operating system. Reads, writes, socket sends, receives, creating processes, scheduling threads, every operating system interaction this tool can record. And if that siscount tool would then go and put this in a file, and you'd have to read that file, it would be a very big file, and it would slow down the system immensely. So instead, what siscount does is actually aggregate this information in the kernel and only generate statistics. And the statistics is the only thing that ends up in user space through, it's not even a file, through a memory buffer. So just as an example, siscount tells me, for my application here, that the top system calls I was performing were open, so opening a file, writing to a file, getting the current time, futex, which is a synchronization mechanism, and so on. And OpenSnoop is another tool that shows you which files your process is accessing. So which files my process is trying to access and what's happening. And if you look on the left here, I've ran a process which keeps printing opening configuration file, and apparently it's failing. And then OpenSnoop on the right is telling me, well, yeah, you're trying to open this file, etc/buggy.conf, and you get a -1, so something's wrong with that file, maybe it doesn't exist. So these are just a couple of tools. Again, they're not specific to .NET applications in any way, but you can use them with .NET applications. You can point them at the .NET process and get information about what it's doing with the operating system. But you might be curious about something that's more .NET specific, so let's look at a slightly different situation. Suppose you have an application with a lot of garbage collections. If you've been to Dina's talk in the previous slot, you know that the GC can really ruin performance for a lot of applications. And on Windows, there are so many good tools available for understanding the GC performance in your application. You don't need any of this low-level terminal stuff, but unfortunately, none of these tools work on Linux, so we have to come up with different ways of doing the same thing. So here's how, and this is a very ugly hack, but it works. Here is how I can take a process running on Linux, running .NET Core, and just count the number of garbage collections that process is doing. There is a tool, part of BCC, called funkcount. It's a tool that attaches to a running process and simply records every time a specific function is called. So you don't have to change your application, you don't have to change your code. You can run funkcount, point it at a process, and you specify which function you're interested in, and funkcount will count how many times that function was called. So it's called funkcount. And you can see here what the output looks like from funkcount. It is not beautiful. It is a hack, after all. But you see the function name here on the left and the count on the right. The names are long, so it got out of alignment. But anyway, this function here, if you manage to ignore all the numbers and the ugliness, but this function zn3, where's the mouse? Come back, mouse. zn3 wks6 gc heap 24 garbage collects generation ej9 gc reason. This is the main function called by the GC when it starts garbage collection. And you can see that function was called, the number next to it is 2,502 times, right? So this is a very, very hacky way of getting this information from the .NET process, but it works. And even better than that, we have a tool in the same collection called stackcount. And it's kind of like funkcount. You point it at a process, you specify a function, but instead of telling you how many times a function was called, it tells you the full stack trace. Every time the function is called, what was the stack trace, and how many times was that stack trace seen. So here's some output from stackcount. This is a stack trace, right? You read this one, like all the others, from bottom, so main, all the way to the top, to slow allocate string, our good friend. And this stack trace was seen 3,155 times, okay? So we can just look at the hottest stack traces, the ones with the highest numbers, and the tool prints them in that order by default, and you can see what is causing garbage collection in my application. Again, a pretty ugly hack that doesn't use any, sophisticated infrastructure, but it's possible on Linux because we have that dynamic tracing. We can take a process which is currently running without stopping it, without changing its code, and just print a message or count or get a stack trace whenever a function in that process is called. And this is a very, very powerful thing that you will find in a lot of the Linux philosophy around profiling and tracing. They assume that you can just do that to any process, and that makes a lot of things very easy. On Windows, we don't have today anything quite as powerful. We have similar things, but not anything quite as powerful. So let's talk now about something slightly more official, which is how you are supposed to get traces or interesting events from the .NET runtime while the application is executing. These were hacks. Let's talk about the more official way. So .NET Core, from day one, Microsoft decided to use a Linux tool called LTTng, which stands for Linux Tracing Toolkit Next Generation. So you can assume there's also an LTT somewhere, and now it's next generation. And LTTng is not part of Linux. It is not part of the kernel. It is something you have to install extra. And so when you install .NET Core, you would usually also install LTTng. The way LTTng works is very similar to Perf, but it is not Perf. It is the third mechanism we talk about today. It has a kernel component, which can read events, and it writes them out to a memory buffer or to a file, often both, to the buffer and to the file. And then you can read from the memory buffer, or you could read from the file and look at the results. So on one hand, it's very similar to Perf in its philosophy. On the other hand, it is not Perf. It has its own format, which is called CTF. CTF is common trace format, but it is only common to LTTng for now. Well, mostly, I'm lying. There are some other tools using it, but you know how it's like. You have 13 formats, and then you come up with the 14th format, and you call it the common format that everyone is supposed to use now. So this is what happened here, more or less. Anyway, LTTng is integrated with .NET Core in such a way that .NET has a bunch of events it can write out to the same buffer and file that LTTng uses. And here's how you do that. So you have to run the .NET application with yet another environment variable called com+enable event log. And this enables LTTng in the .NET application. If you don't do that, you will not get any logs written at all. And the reason this is not on by default is that it has a certain overhead. Again, you have to measure to determine exactly how bad this is, but there is an overhead to just enabling the tracing infrastructure in your process, which is why it's not on by default. Once you've done that and your application is running, you can then use the LTTng command line tool to create a recording of what's happening in your process. And specifically, all the .NET events are under this .NET runtime provider, and you can specify specific things here instead of the asterisk. For example, garbage collection started and ended, JIT compilation started, ended, new thread was created, a thread was destroyed, a thread pool thread was created or destroyed, an assembly was loaded, unloaded. So you have, probably 30 or 40 different events you can trace from this, from the LTTng provider in .NET Core. If you're looking for the same thing on Windows, again, this is event tracing for Windows. This is ETW, but we don't have ETW on Linux, so what Microsoft chose to use for this part was LTTng. Now, the result of this recording is a file. Like I told you here, it eventually writes into a file, and you can open that file on the same machine or on a different machine, and even a different operating system. You could, in theory, take that file, copy it to Windows, and open it there if that's your thing, right? But essentially, that file is a list of events. So here's a scary slide, but it's just events. And you can see some examples in this slide and a couple of next. These are some of the events in that recording. So one is called GC sampled allocation high. This is an event for tracing allocations. So every time an object is allocated, roughly, you get an event. Another example is exception thrown. So every time an exception is thrown, you get an event. Now, of course, you don't have to parse this text in the command line. There are tools that can show it for you in a nicer way. And of course, because it's text, you can just parse it yourself. So for instance, using a little shell magic, you can get the top allocated types in a recording and see that the top type is byte array, next one is string, and so on, just by playing around with the text in that file. And then you can use it to generate charts or whatever. And so, because everything is just simple text at the end, it is fairly easy, and that's the Linux way of doing things, it's fairly easy to parse it and display it in different ways. So that brings us to the last thing I wanted to talk to you about, and we haven't touched on yet, which is debugging, right? You've written an application, it's running in production. If it has performance problems or memory problems, maybe you have some idea on how to look at it. But what about crashes or memory leaks or hangs, things that really require a debugger? So for now, there is no magic, great, beautiful debugger that you can install on Linux and debug your .NET application. And probably the closest thing to that is using dump files. So you can take dumps of your .NET application and then analyze those dumps. But that also isn't quite easy, so I have a couple minutes to talk about that. So first, just as a reminder, I guess you might have used them on Windows. They also exist on Linux. Core dumps or dump files or crash dumps, these are all just names for the ability to take a running process, a process which is currently executing, and take a snapshot of its memory and save that to a file. So think about it, as frames in a movie. The process is running, you stop the movie for a moment, save that image into a file, and the process keeps running from that point. And this is naturally useful for a lot of things. One is crash analysis. So if the process is crashing, it will save its state to a file before exiting. So that's useful. But you can also use it for memory leaks, for hangs, for a lot of other things. When you don't want to stop the process, attach a debugger, place breakpoints, because you can't afford to do that on a production system, but you can stop it for just a brief moment, generate a file, and then the process keeps going, but you have that snapshot in your hand. So to create dump files on Windows, again, there's so many tools. We could probably fill 3 slides with just the names of the tools for generating dump files on Windows. On Linux, there's also a couple of options. There's a couple of things you have to know first, which is that even if everything is configured correctly, there are some general system-level configuration switches that you have to toggle. And I'm not going to explain each one. It's just something you can read online. But then to create the actual dumps, there are 3 general tools. One is gcore, which is not .NET related. It's a command line tool. You point it to a process, you get a dump file. Core CLR itself comes with a tool called create dump, which is pretty useful, and it was built to create dumps of .NET processes, so there's that. And finally, there's even procdump, which you might have seen on Windows. It now has a Linux version as well. I think it was released a year ago, maybe a little more. So there's multiple options for generating the dump. But now what? You have that dump on disk. So the way you're supposed to analyze dump files on Linux is using the lldb command line debugger. There is no Visual Studio on Linux yet. And you can't open dump files generated on Linux in Visual Studio on Windows yet as well. So your next best thing, and it's really not a very good thing, but that's the only thing you have, is lldb. It's an open source debugger. It is wonderful, but it's not so easy to get used to. You might have seen WinDBG on Windows. It is roughly as hard to use, or as easy to use, if you will. So you run lldb, and you tell it two things. First, which executable generated that dump file. You have to say that explicitly. And then, what is the dump file, where the dump file is. Then lldb opens, and you type in the bt command, which is backtrace. Give me the stack trace of what that process was doing when the dump was generated. And the stack trace sounds bad. You know, abort, proc end process, unwind, manage exception, pass one. It sounds like it's crashing. But where? Here. And remember, the same issue from earlier, the stuff we care about is disguised by numbers. We don't have the debug information available to the debugger to translate these addresses to C# function names. The C++ stuff works, you know, but that doesn't really help us. So we have to use an extension. On Windows, you might have heard about SOS, which you use with WinDBG. On Linux, we use Lib SOS, which works with lldb. It's the same code, it's just the cross-platform version of SOS. And you load it into lldb, much like you load SOS into WinDBG, and then you have a bunch of commands that you can run. Dump an object, print all heap objects, show the .NET threads, print the .NET stack trace, so many beautiful things. So let's quickly walk through a last example, and then we'll wrap up. So I've ran my application here, and it crashed with this message. Let me zoom in on the relevant parts for a bit. It crashed, application exception, task crashed, and this is the stack trace I got, which looks a little weird. So this is my code, handle unhandled exceptions, but this is .NET code, and it looks like the finalizer for some class called task exception holder. You might have seen it before, but anyway, it's crashing there. And then it aborted, and the core was dumped, so we have a dump file. All right. I open it in lldb here, and this is not something you have to actually read. This just has a list of threads, and it tries to tell you what the assembly they were running. Not interesting. So moving on, this is the stack trace I was showing you on the previous slide. And again, remember, this here is the C# code we care about. OK, so what do you do? I'll skip a bit because we don't have a lot of time. But eventually, I can get a .NET stack trace using the CLR stack command of what that process was doing. So remember, handle unhandled exceptions, published unobserved task exception holder finalize. All these methods, all these C# methods are now visible in the debugger as well. But what's interesting is this doesn't tell me what code actually caused the exception. If you look at task exception holder, you'll see that the only purpose of task exception holder is to crash the process if you have a task, a TPL task, which had an exception, but you haven't seen that exception yet. So this isn't telling me much. So now we can maybe investigate other objects on this stack to try and understand what's going on. And specifically, again, we don't have a lot of time, so I'm going to be quick about this. There is this E over here, which looks like an event args object, and this is the address for it. So I'll just ask the debugger to show it to me, and this is an unobserved task exception event args indeed, and one of its fields is an aggregate exception over here, and this is the address. And we can take that address and display it and find it's an aggregate exception. And I don't really expect you to be able to follow this right now, but you can look at the slides later. And at the end, it brings us to the real exception that happened, the real exception that happened in this process, which is here, invalid operation exception, the update could not be completed coming from this stack trace over here. And I know this is nothing like using Visual Studio to debug your code, but it is doable. And the only thing I promised you today is that it would be doable, not that it would be easy. And it's very important to not get confused between the two things. So I have a quick checklist here of what you would have to do if you were to prepare your environment for profiling and debugging. I will, of course, share the slides with you. And so just to wrap up real quick, then we have a couple of minutes for questions. We've seen how to do CPU profiling, so use perf to understand what the process was doing, and how to visualize that information with flame graphs. Remember those beautiful flames. We talked about using tracing to look at garbage collections or exceptions being thrown and things like that. And finally, we talked about core dumps a little as well. I have a lot of references. Again, I'll share the slides with you. And there's blog posts, there's a lot of material online. But still, remember, a lot of this relies on slightly undocumented features. And if you want Microsoft to make this a little easier, and if you really want them to do that, you maybe should say so. And so, raise issues on GitHub, complain, implement things on your own, and maybe we can make this all a little easier. So thank you very much. We have a couple of minutes for questions. Thank you. Yes?
Who have questions?
Sasha, first of all, thanks for your speech. I got a question. You told us about how to take a dump, but is it some easy way to compare dumps? From maybe it was some increase of some type, so...
Right. So you're asking how can we compare dumps, but specifically how to compare the heap objects, right?
Yes.
Yes. So there is a command called dump heap, which has a statistics mode, and it will print out, it was on the slides, it will print out for each type how many instances and how many bytes you have. And so you can just print that to a file and diff them, right? It's not that bad. There is nothing automated that does that, but I mean, you and I could write a script probably, right?
Okay, thank you.
Yeah.
Anyone else?
Okay, but that, by the way, is what I was talking about. If you need this stuff for your work, not just in theory you wanted to hear about profiling, which is acceptable, but if you need this stuff for your work, I definitely believe that Microsoft should also invest some work on their end to make it easier. So this is why I'm saying complain, make a noise, tell people what you're doing, share your tools and your approaches, and then maybe we can make this a little easier for everyone. All right, if you have any other things you want to talk about, you can also catch me in the expert zone a little later. So again, thank you very much for coming. Enjoy the conference.